Thank you. Thank you, everybody. Before I begin, I'm going to give over a few minutes to Nick Carey from blockchain.com, who's going to be building out a fully fledged Polkadot governance UI as part of their wallet.
Yes, so thank you everyone. My name's Nicholas Carey. I'm the co-founder of blockchain.com, and it's my great privilege and honor today to announce that we are going to be forming a partnership with Polkadot, the flagship project of the Web3 Foundation. We have over 41 million users around the world that use blockchain's wallet to have self-custody over their private keys. And our mission over the last 7 years has been to make it easier for people to send, receive, secure, and exchange things that are valuable to them. So it is majorly mission aligned to be able to work with Gavin and Rob on this project together. In the very near future, you're going to be able to send, receive, and store your dots inside of blockchain.com wallet, as well as integrate the voting proposal systems within the blockchain.com interface. So we were tremendously excited, and I wanted to be the first to share it with you here in Berlin. Berlin is the place where we come to for inspiration to think about how we design and defend our future, and we don't accept the status quo. And I think it's one of the things that's so invigorating about returning to this city. And I was talking to Rob a little bit about the community before we came out here, but when Snowden was talking about just how impressive the work that's being achieved here is, I'm reminded of that every single time. So I didn't want to take up too much of Rob's time today, and he has a really impressive presentation he'll be sharing with you in just a moment. But on behalf of the whole team at blockchain.com, it's a really exciting day for us to be able to announce this partnership with Polkadot, and we're looking forward to working with Gavin and the rest of the team at the Web3 Foundation as we roll this out. So 41 million users around the world will soon have access to Polkadots. This is also going to help us bring a new era of governance to the internet, and we need to get these tools in the hands of regular people. We need to train them, we need to onboard them, and this is going to be a major step forward toward that vision. So thank you guys very much. I'm going to hand it back over to Rob and jet to the airport now. So thank you, Rob. Yeah. Thank you, Gavin. Great job today.
Thank you very much, Nick. Right, it's really exciting stuff. Today I'm not going to be talking too much about governance. What I'd like to do is get sort of an overview of the kinds of problems that we're solving with Polkadot's research and development. Roughly, what it actually takes to put together a sharded, heterogeneous blockchain system, something that can really scale. Because at this summit, you're going to be hearing, and you have heard about lots of projects that are going to have humanitarian, societal, many different kinds of powerful impacts. And the thesis of ours, as well as those here, is that blockchain technology provides an amazing way to actually leverage effects and consequences automatically upon parties who are participating in some sort of contract. And this is an extremely powerful tool, but in order to make use of it, it has to be scalable. And the way that we think about research is from an absolutely very practical standpoint. Many of you in the room may be developers, but the way that I look at coding is something akin to, say, carpentry of years past. It's a very mechanical pursuit. But it's a powerful tool when combined with the right patterns of thinking. If you would look at, for instance, Leonardo da Vinci, he would craft beautiful machines and design them out of wood, but it wasn't the fact that he knew how to build things out of wood that made his invention so impressive. It was the fact that he was always thinking of how to do things differently. And this is the approach that we take with research, is essentially to take developers and to equip them with the tools to build something that is novel, not just to be, for instance, copying from a spec, but to be actually actively constructing. And this is our ideology. So I'm going to structure this act in this talk in 4 acts. The first act is the motive. So what motivated us to build Polkadot, and why do we structure it the way that we do? In any kind of engineering system, you have this property that specialization breeds optimization. That's, I think I said that for the first time at the Web3 Summit last year, so I'm going to return to my roots here. But essentially, if you construct a solution for a particular problem as opposed to trying to solve a class of problems, you can employ optimizations that simply would not be present if you try to create an absolute general solution. And this applies absolutely to blockchain systems as well. For instance, you have classes of problems where you want to store your data in a particular way or do some computation that gives you algorithmic improvements over if you would try to have all applications use the same storage formats and means of computation and metering. In that sense, specialization is a crucial part of what we try to deliver with Polkadot, is that it allows blockchains to conform to a particular goal. The other aspect is that specialization will allow you to much more strongly contain the ways that your application can be interacted with, and that provides security. Indeed, it also provides sovereignty. The idea that a blockchain is not subject to rules that are above it. And we have designed technologies, for instance, in the form of substrates pluggable or hot swappable consensus systems that you can actually change the consensus algorithm of a blockchain while in flight. So indeed, a blockchain can decide that it does not agree with the method that is currently being used to secure it and to swap that out for something else. Of course, specialization is important, but if you have only a single specialized system that exists in its own bubble, that's not going to be particularly powerful. What makes blockchain systems powerful is composability and the ability for network effects to occur. That you have many different protocols that can just plug and play and interoperate with each other. And if you create specialized silos, that's not going to be the case, which is why interoperability is a key part of what we aim to deliver. You can think of it, rather than forcing all chains to obey the same framework, in the way that every person's brain is structured completely different. So you have different neural associations with different concepts, but we have language, and that allows us to communicate. You can think the same way about how blockchains interoperate. They don't think about concepts the same way, or even have necessarily the ability to think about all the things that the other blockchains are thinking about. But if you give them a common language, they can interoperate and communicate and share those ideas. And that is extremely powerful. I'm going to skip this slide in the interest of time. Yes. So, the most difficult challenges, I would say, are about creating interoperability where security is actually possible. So if you think about how consensus systems for blockchains are structured, typically you would say these economic identities are associated with the security of this chain. So, whether that's the miners or some stakers, one of the most difficult things to do is to get two chains to talk to each other. So, for instance, you could have two chains that are secured by different consensus algorithms, and they might each have a notion of economic finality, but everything has a price. And the economic finality of one may be reverted by an adversary purchasing, some of those stakers or some of those miners, and reverting one chain that may have sent a message to another chain. So what can happen there is that you have an effect without a cause. The finality and the cause have been reverted on one chain. And one of the main goals of what we've been trying to research with our consensus algorithms is a way of uniting all of these chains under the same source of security. In essence, that to 51% attack one of those chains, you have to 51% attack all of them. And that means that you can, one, do interoperability very easily because you have near instant latency. The fact is that you don't have to rely on messages reaching finality before they're transferred. And that it's safe in the sense that you don't have to worry about your message that you've received and that you've acted upon being undercut from you by external actions on another blockchain. You can think of Polkadot as a network interface for blockchains. So Polkadot is very, very agnostic as to what kinds of computation are actually being done, but it allows them to communicate. And to run very quickly through some of the terminology that we're going to be using, we have the idea of parachains, which are these specialized blockchains. We have the relay chain, which connects and secures those blockchains. It basically maintains the message queues and provides the security that transfers down to them. This is the main object, the main protocol that we actually try to achieve consensus on. We also have another kind of chain, which you could think of as a bridge chain. From the perspective of Polkadot, these are actually not treated specially, but they are, in fact, simply chains that know how to interpret the finality of another chain. And this of course, is subject to the caveat which I mentioned earlier, which is why for bridges you have to be very, very cautious when dealing with assets that have been bridged over from another chain. We have a number of economic actors. One of those is collators. So what we do is we separate the construction of blocks from the validation of blocks. And the collators are the ones who construct blocks. They are familiar with the internal workings of a particular state machine and send those to validators, whose job it is to actually attest to the validity of those blocks. And those validators are sort of able to interpret proofs of validity for all of the registered parachains, and they aren't necessarily native to any one of them. There have been a lot of talks about Substrate so far. It's a very, very exciting piece of technology, and this is how I would say it fits into the stack, is that Substrate is a tool for building these blockchains, but Polkadot does not rely on it. Of course, you would be hard-pressed to find other SDKs that are quite as versatile in terms of building the state machines that you would need to build a parachain. But Substrate is sort of an independent entity from Polkadot that can be used to build any of these kinds of chains, including the Polkadot relay chain itself. We've been eating our own dog food there. This is a really cool picture. Like whoever did that was pretty cool. This is the fortress. So I talk about the consensus system, essentially what underpins the security of Polkadot. There are essentially, I would say, two classes of consensus algorithms that are used in blockchains. So the very first one that people would have come to mind is proof of work consensus. And this is a major innovation because it's the idea of this probabilistic finality, this probabilistic agreement, that before waiting for absolute agreement on something, that you continue to build and optimistically sort of build on the long chain. You know, in the case of bad network conditions or adversarial nodes that are selfishly mining, this does revert back to it ends up being slower because you have lots of little forks and reorganizations and things, but it's very interesting as a tool for getting progressive consensus, where every block that's built contributes to the finality of all of those before it. On the other side, you have these classical consensus algorithms that aim to achieve full consensus on something in a round before moving on to the next round. And what this is good for is getting a very fast degree of high security. You know, with the one confirmation in proof of work, it's very likely that things will be reverted. Whereas with one confirmation from a classical consensus algorithm like Tendermint, PBFT, or Grandpa, which is the one that we've invented and implemented, that means that you know already that it's sort of reached the maximum security threshold. So the hybrid consensus model we find is very good for the combination of optimistically high throughput, but also fast finality. This is a diagram of how Grandpa works, basically. You could think of it as a formalization in some sense of the kth ancestor principle of probabilistic finality, which is saying, like, if you ignore the last 6 blocks that everybody has, they all have the same chain. And what this does is it's a consensus protocol for figuring out what's the common ancestor of all the consensus nodes best believed to be best chain. And then you finalize that chain, and every chain from that point on has to contain that prior chain. Babe is quite similar to a consensus protocol called Ouroboros Praus, but it has a couple tweaks that are can be considered with a very practical mindset. So the first one, what this diagram explains, is the relative time aspect. So many consensus protocols that do this kind of time slot-based leadership, so we'll do it like this. They'll say, this time slot, or all time is divided into time slots of 4 seconds, or 6 seconds, or whatever, and we select a leader for each time slot. And you're like, well, that's great, but whose clock are you using? And that's sort of the caveat, because it kind of implies that for it to really work, everybody has to be connected to the same NTP server. And that's obviously a centralized point of failure. So what we've done with Babe is, one, we've come up with a way to approximate the time slot that is currently happening just based on when you're seeing blocks that claim to be released at a specific time. And the other thing is we combine that with a method for actually having roughly fixed and constant block times, because from an engineering perspective, this is extremely viable, since you know how much time is going to be spent that you can reasonably spend constructing the next block. You don't have to contend nearly as much with variance, and that lets you push block times on average lower. Yeah. So I talk about one of the main pieces of the Polkadot protocol, which is the validation function. And the validation function is essentially, it's a piece of code that's registered on chain, and it behaves like this. So you put in the last header of the parachain, you put in some info about the Polkadot relay chain, and you put in some proof of a state transition, which is like the transactions that were in that block, all the account data and proofs of that account data actually being the account data necessary to execute those transactions. And then you get either, yes, the new header, or you get, no, that was bad, that was garbage. And collators are the ones who actually construct this block data, and that never ends up on chain. The main job of validators in Polkadot is basically to sign statements saying, I checked this validation function against some claimed parachain block, and the validation function said, that block is good. They sign that statement, and if you get enough of those from the people who are assigned to that parachain at any time, you advance the parachain. There is a caveat. So 1/3 of validators can lie, right? We have a Byzantine assumption, which is that up to 1/3 of validators can behave arbitrarily. They can double sign stuff, and basically with a consensus algorithm, you're typically equipped with an honest majority assumption. But you have to, in a permissionless setting, couple that with some kind of economic incentives to prove that rational behavior is honest behavior. Proof of work, that's fairly simple. In proof of stake systems, what you do is essentially you force those who would like to participate in consensus to bond some money for a relatively long period of time, during which they're going to be participating in consensus, and if they do something wrong, then they get slashed. They lose, a big chunk of their money. That's, that's bad. That unifies the rational and honest behavior. So we have this 1/3 of validators overall are Byzantine, and the main problem, this is really the biggest issue that any kind of sharded blockchain system is going to face. This is the #1 problem, is that once you start to subgroup this set of all validators, you can sample subgroups that are majority or entirely malicious. And that's very, very bad. So what we need is essentially a way to provisionally accept things on the chain and then allow others to check in the background. We call those fishermen, to check that that state transition was actually good. And the most important thing is that the data necessary to check if a parachain block is good is available. That if I decide, hey, I want to, I don't trust these validators, or I'm just checking every block that happens on this parachain, I'm actually going to go fetch this data and check if the validity function says this is good. If that data is unavailable, then nobody can check and it's completely unsure. So we want to make sure, one, that it's available, and two, that it corresponds to valid state transitions. So the scheme that we came up with is essentially using a technology called Erasure Coding. And this has been around for a long time, but what we do is for every parachain block proof, the proof that the parachain block is a valid state transition, we split it up into n different pieces, so one for every validator, and any f+1 of those pieces can be used to recover the entire parachain block proof. F being the amount of validators who can be malicious. So, it's not only the malicious validators who will have pieces. You always get at least enough pieces into the hands of honest nodes, because there are always going to be, even in the case of network partitions, a group of F+1 honest nodes. If those pieces actually exist, they're going to have them. And we further provide some guarantees for data availability by having additional rules for consensus. So for instance, validators are going to keep track of whether they got the piece that was assigned to them for some particular parachain for every parachain in every block in the recent chain. And if they don't have that, they're not going to vote on finality for that block. They're going to say, well, I can't guarantee that I've done my bit for availability here, so I won't vote on finality. And finality requires that 2F+1 quorum. And additionally, they're going to refuse to build on chains that don't have all of those pieces, except for a very small portion at the very end of that chain. And what that looks like is something like this. So if I've gotten my piece for parachains A, B, and C in these two blocks, then I'm going to vote on that chain. But I won't vote on the third or fourth block because I haven't seen all the availability pieces that I was supposed to get from parachains A, B, and C. In terms of building rule, we can say k equals 1, and I'll say, OK, I'm willing to build on top of block 3 because I have an allowance of 1. And if we say k equals 2, you'd say I'm willing to build on the fourth block because I have an allowance of 2 blocks in the most recent chain that I don't have all the pieces for. And this gives us really pretty good assurances about, if a block is finalized, that means that 2/3 plus 1 of the validators thought that all of the data necessary to verify those blocks is available and that they have their piece. And it also gives us a very good optimistic assurance that the longest chain is the one that's most likely to have all data available. It also tells light clients in an availability scheme who they should be asking for pieces of data, based on who's voted on finality for a chain and who's built on blocks in a chain. So the fourth act, because programmers start at 0, is about the watchers, the fishermen, those who are looking for that misbehavior. So as I mentioned before, this is a proof of stake system. And there's this nice quote. Well, I'll get to that in a second. Essentially, we've tied validators to crypto economic stake, and they're going to be slashed if they, for instance, issue an attestation on a parachain block that is bad. And the people who actually discover that, so first the attestation for the bad block goes on chain, and then you have fishermen who are watching, and they're not registered in any way. They just watch to see what's happening on parachains that they care about. And it only takes one of them to discover the fault and to submit an irrefutable proof of misbehavior that leads to slashing. So I'd like to talk a bit about essentially the role that light clients play in this, because the fishermen are not likely to be able to run full nodes for every parachain, or indeed perhaps even that's beyond the reach of a regular person to run a full node for 2 blockchains at once. So what a light client does is they verify the consensus data, but they don't verify the state transitions. In essence, they don't execute transactions, and they can't be trusted to repropagate data, so they shouldn't be doing that. I mean, you could write a light client that repropagates data, but it wouldn't really help the network because they haven't verified a lot of that data. The only thing that they can really have a strong assurance on is that consensus has been carried out correctly on some header chain. And that allows them to cryptographically fetch any kind of data associated with that chain that they trust. And they fetch that data on demand from full nodes. So Substrate has been designed light clients head first. I think this is super important because it's very, very difficult to retrofit a working light client onto a code base that was not designed with that in mind. But when you think about it from the very first step, you can build that in parallel with the rest of the software. And Substrate, fortunately, I think we did that right. So it's not only immensely valuable for fishermen, but it's also extremely interesting for your typical laptop, mobile devices, embedded devices, your electricity meter, kind of anything that wants to access the blockchain but doesn't need to use a huge amount of data. Like you can plug this into IoT and probably come up with compact finality proofs where you send it a couple kilobytes of messages every day and that's all. But it's especially important as we move into a world for sharded blockchain systems, which is essentially if you have an application that's spanning multiple chains, you're going to want to have your sort of application shell running a light client for some, if not all, of those chains. And that's, of course, not viable to do at all if you have full nodes. So, a nice library that lets you write a piece of JavaScript code that's like, okay, I want to run a light client for this chain and this chain and this chain, and it kind of uses a little bit of resource computation in the background, but not actually that much, is very, very powerful. And one of the main things that you have to take into account with this light client protocol is that you want to minimize round trips as much as possible. When you have user interfaces, 100 milliseconds is kind of the hard cutoff for how long something should take. So we've designed the light client protocol for fetching that on-domain state data to be as efficient as possible in that regard. I won't go too much into details here, but it has to do essentially with pipelining, that sometimes you'll make a request, and then based on the response of that request, you'll want to fill out another request, and then so on. So the idea is to push as much of that over to the server side of whichever full client is giving you that information as possible, so that you don't actually have to make the round trips. The round trips kind of happen internally. And there's a cool trick that you can do essentially by sending over a WebAssembly blob to be executed and metered to actually do that additional computation. So if you think about what fishermen are really doing, is they want to be watching the relay chain and what's going on the relay chain with respect to a particular parachain. They don't need to be a full node for that. They just need to check the consensus, see which blocks are being built upon and finalized, and then get small state proofs of, oh, these were the attestations that were issued on this parachain. And they probably want to be a full node of the actual parachain. And that is fully doable as long as you have the ability to run one light client. I'll leave it off here, and if you have any questions, please let me know. There are, unfortunately, due to time, there are a bunch of topics that I'd really, really like to go into and chat about if you find me after. For instance, we didn't even get the chance to talk about how networking is going to work. You have all of these different economic actors who are going to be communicating somehow and synchronizing many different blockchains and passing all kinds of different consensus messages, but whose result has to reach untrusted nodes, i.e. fishermen, so that they can check that stuff. The networking of a sharded blockchain could be an entirely different talk. And I think if some of you are interested, we should be having that conversation today or in the next few days. There are also more topics, but unfortunately we don't have time. So thank you very much.